know that we can do this problem without calculus, right? That's not the point here, but just to demonstrate to do this with it. You know that's the case. And we have a point which is 3 and 4, and hopefully you can calculate that without my help. What's the slope of this? 4/3, right? Then what's the slope of this perpendicular line? -3/4. Then point slope form, right? So it just naturally happens. So that's not the point. I'm taking an easy example in order to demonstrate the new procedure here, calculus, okay? So I'm giving you a calculus lesson using algebra example. So instead of doing it that way, we use derivative. Okay, so first, we need to find the function, which is this. Good? Too much algebra? If you have a function like that and solve it for y, of course, plus or minus is missing, isn't it? What does that mean then, if we are missing plus or minus? This one at the moment is the upper half semicircle, get it? And then we'll have to do this one separately, otherwise it's not a function. You get it? Okay, and it's easier if we write it like this, 25 minus x squared and then 1/2 power a. Let's review chain rule, but I like to do whatever I showed you on the video, because video, for some reason, nothing beats live performance now, doesn't it? With the mistakes and all. So this is kind of what happened, and you don't have to do this ever again. I mean, your book makes you do it because it's healthy. And later, when we have something called antiderivative, this knowledge, this skill, this justifies the chain rule and explains why it works the way it does. This is a big deal, okay? So see this, I'm going to rewrite this, 25 minus x squared to the 1/2 power, and we substitute u, because at the moment we cannot take a derivative unless you know the chain rule. But why does it work? U is equal to 25 minus x squared. So inside function, remember composite function, outside function, 1/2 power, inside function. Okay, then I make a substitution. So this is u to the 1/2 power, which is much easier derivative now. And we take dy over du, which is 1/2 u to the -1/2 power. So far with me? And this is where it gets weird. Dy is equal to 1/2 u to the -1/2 power du. So far so good? Like that was the difficult part to swallow. They are fractions, they separate like that. Well, yes and no, depends on which mathematician you talk to. There are people called analysts, okay, analysts, but I call them analysts because that's kind of how they behave. They are the ones who are saying, no, you can't do that. No, we have to prove everything in terms of epsilon and delta. So that's no. But then, do you remember a mathematician named Gauss, also known as father of mathematics? I mean, he gave so much of calculus, multivariable and everything. And Gauss did it like this, with this thing called infinitesimal. Okay, so if it's good enough for daddy of mathematics, it is good enough for me. So I believe in this. Okay, and then we divide both sides by dx because it works every time. So what we have is dy over dx is equal to 1/2. What is u? U, remember, is this thingy. Substitute it right there. You get it? So u is 25 minus x squared to the 1/2 power, or -1/2 power. You notice that this thing hasn't changed, right? It's just the outside thing. And then what is then du over dx? We kind of need it here. We get it over here. Du over dx is, of course, -2x, right? And you take that and shove it right here. You get it? You get it. Feel free to use microphone. Alrighty then. So what we have is -2x. Good. You with me so far? That's kind of what happened on the video. Now, let's come back and do this in one shot then. dy over dx here now is, think turducken, right? Outside function, turkey. So it's 1/2 thingy negative 1/2 power. You get it? That's kind of what we did here, which eventually becomes this. You get it? And inside, the duck is still cold. And the inside thingy, which is duck, we wrote duck now. And that's negative 2x. Do you see this is precisely what we have here? Okay, you don't have to show me this ever again. This is just healthy exercise, and remember it later when we do antiderivative. But other than that, we'll just do it the short way now. You with me? Okay, we'll simplify this. If I write it like this, is it too much algebra? You got it? Okay, let's evaluate this function because we need a point and we need a slope. Watch this. Okay, you can just write 3 because in this case it's obvious. There's only x as a variable, but this might happen. And you have negative 3 over 4 now? 8? Say yes. Okay, so y minus 4 is equal to negative 3 over 4 and x minus 3. Converting y is equal to negative 3 over 4. X, is it 25 over 4? Let's check. Oh yeah, that y-intercept looks like 6 and 1/4. 8? How about that? Okay, so that's one of the answer. We have to do this again, huh? Oh boy. However, what is the other function? Isn't it just this? Does that look exactly same as what we had here? Yeah. Only difference is negative sign. So we can pretty much recycle our work, eh? And that recycling our work is this. Positive x over square root 25 minus x squared. How about that? Good? And I'm pretty sure you can take it from here. Alrighty. Okay. Now, there is another way to do this, and the other way is this. Let's talk parametric functions. You remember forgetting parametric functions? Like when you first showed up here, I taught you this, and we played with ellipse and hyperbolas. You feel the circle? Do you not feel the circle? Okay, and then how did we take the derivative of this? Well, we didn't, but let's just take a derivative with respect to t. So this becomes negative 5 sine of t, and this thing now becomes 5 cosine of t. You with me? Now, then, what is dy over dx? We need that. That is a slope in this curve, right? This is still x and a y, eh? What is dy over dx? Could it be this thingy over this thingy? I mean, fractions simplify like that, but could we get that lucky? The other word, in other words, is this over that. Could we get that lucky? What do you say? Yes or no? Answer is yes. What? But we still have to justify this, right? So how do we justify it? I'm going to semi-prove it here in the corner. Say x is equal to some function of t. And y is equal to another function of t, right? In our case, this is cosine, and this is like 5 cosine, 5 sine. You get it? Say yes. Okay, let's say we want to eliminate parameter t and have y as a function of x. Then we have to solve this as inverse function. That makes sense to you? In our case, that t would be inverse cosine of x over phi. You know what I'm saying? So we can, if x is a function of t, then we can make t as a function of x by finding the inverse, eh? Say yes. Okay, then we take that and substitute it right here. So what we have is y, which is a function of g, which is now function of x. How about that? Composite functions, eh? Okay, let's just keep track of what everything is. This right there is our t. You get it? So y is a function of t and t is a function of x. Good, good, good. Now we take a derivative. So dy over dx. Let's first write it in Newton's notation because that's easier to understand. That would be g prime and then f inverse of x. Remember, unchanged, our chain rule. Then the derivative of inside function. Good. Say yes. But if we rewrite this into Leibniz notation, it's much, much nicer. This thingy, remember, this thingy is our t, right? So the derivative is with respect to t, isn't it? So that's dy over dt. And this thingy, of course, is dt over dx, eh? Because this is a function of x, t, this is our t, or derivative of t. You get it? Now, wow, this is a nice fraction. These are just fractions, so it ends up being, how about that? Ain't that nice? Okay, so that's kind of proof, well, semi-proof. Because you know the analyst will never accept this, right? You cannot really use infinitesimal to prove anything, whatever. But this is good enough for Gauss, all right? Okay, well then, now we are ready to do this. So this thingy is just this thingy over that thingy, which is of course negative cotangent t. Too much algebra? Too much trig identity? You got this? Okay, that's nice. And we have to evaluate this, right? So what is dy over dx evaluated what? You cannot put 3 anymore because look, this is a function of t. Ew. So at t is equal to what? Somebody give me. T is this angle, of course, right? Somebody tell me what that angle is. Feel free to use your microphone.
Inverse tangent 4/3.
Oh my God, who was that? Y'all got it? Tangent of t at the moment is 4/3 now, isn't it? So that's inverse tangent, which of course is now inverse cotangent of, cotangent of inverse tangent of 4/3. Too much trick? Y'all got this? Can you do this? And then you move on to do exactly the same thing. It's point-slope form. But here is something quite scary, and some students never understand this. What is this then? Well, can't you just take a derivative? No, you can't, because look at it. This is cotangent of t, and we are trying to take another derivative with respect to x. See the problem right there? Okay, how can we do such a thing then, eh? Well, we have to examine this thing a little bit. That's kind of what it is, right? Leibniz notation rules. Okay, and then let's just look at it a little more in detail. We kind of figured out what dy dx is, and that's in negative cotangent t, isn't it? Oh, we are still stuck. Do you remember that kind of chain rule we did? We let another thing, z, we'll just, cosine, like that. Cotangent t. How about that? If you make that substitution, then this thing becomes very nice. It's just this, isn't it? Which of course is, let's just stare at this for a few seconds. This z is a function of t. X, of course, is a function of t. Can we just repeat the process all over again? Instead of x and y, now we have x and z, z being negative cotangent t. You get it? Yeah. So what that becomes is, this is dz over dt over dx over dt all over again. Okay, dx over dt, we already figured it out, and so we don't have to really do it again. We recycle our work. Negative 5 sine t, and dz over dt. Somebody then can tell me what is the derivative of cotangent. You might have to derive this on the test by evaluating difference quotient, you know. You should at least know what it is. It's negative cosecant square, so it becomes positive cosecant square t. Therefore, the whole thing becomes negative 1/5 cosecant qt. How are we doing? Okay. Are we good? Now we can develop this thing a little further. Suppose we have an ellipse. U. Okay, then how are you going to find the derivative? See, circle idea was nice, but circle is kind of nasty. But this equation, solving it for, let's do it. Y is a function of x is kind of nasty when you have something like ellipse. And then let's say somebody told you to find when angle is pi over 6. What's that tangent line? Huh. Okay, let's do it. Say this is 5 and this is 3. How about that? So our parametric equation is 5 cosine t and y is equal to 3 sine t. Exactly same as before, except on y side I have reduced it to 3, so it flattens it. Then dx over dt is exactly same as before, sine t, and dy over dt is 3 cosine t. So dy over dx is this time negative 3 over 5 cotangent t. Good. Good. Now, then over dx and find the equation of the tangent line, right? So first thing we do is find dx over dt, and that is 1 minus cosine t here. And we find dy over dt, and that will be 0 and negative, negative, so positive sine t. So far so good? Okay, then we find dy over dx, which is this thingy over this thingy, right? So we have sine t over 1 minus cosine t. Good. And while we are at it, we evaluate it at pi over 3. So put pi over 3 here. No, t is equal to pi over 3. Good. And sine pi over 3 is root 3 over 2. And cosine pi over 3 is 1/2. And that gives you root 3. So far with me? Now, we still need a point. In order to use a point slope form, we need a point. Where do we get the point? We get it from here. You get it? X is equal to 1 minus, well, pi over 3 minus root 3 over 3, 2. And our y is equal to 1 minus 1/2, isn't it? Which is 1/2. That becomes our point. So then point slope form is y minus 1/2 is equal to root 3, and then x minus pi over 3 minus root 3 over 2. And then you convert that into slope and intercept form. You get it? Okay, now the question? Difficult one, 49. Okay, 49, this procedure, they're trying to teach you what to do. Forget it, I just do it, ABC together, okay? So A is this. We find dx over dt, which is 2t plus 1a. Say yes. And then dy over dt, which is cosine of t. So far so good? Okay, then we find dy over dx. Once again, that's this thingy over this thingy. So we have cosine t over 2t plus 1a. So far so good with me? We are going to call this thing z. Okay? Now, let's think about it. Maybe I should rewrite it here. So brand new problem. X is equal to t squared plus t, and z is equal to, what is it, cosine t? Cosine t over 2t plus 1, right? Then all we have to do is take dz over dx. You know what I'm saying? Now, dz over dx, of course, is same thing as this thingy, isn't it? And in fact, that is what our second derivative is. You see the procedure? I'm going to move it down a little bit here. So this thingy, it really is our second derivative. How about that? Okay, so in order to find dz over dx, it's exactly the same procedure. We need dx over dt. We don't have to do it. We have done it already, but just to prove a point, it's exactly the same thing all over again. And dz over dt, which unfortunately is a quotient rule. So denominator square, and then u prime negative sine t times 2t plus 1 minus, and then u, and then t prime. Good. Okay, now what we want to do is this thingy over this thingy. You get it? So what we have now is negative sine t times 2t plus 1 minus 2 cosine t, all divided by 2t plus 1 cubed. Hopefully that's not too much algebra, right? Let's turn, but these two have to be the same thing. And then remember, radian on a unit circle, say that's a radian angle. It really means that physical distance is radian, isn't it? So it's still idea of distance over distance. You get it? So that gives you at least the same unit, so that this thing does not come with weird unit like that. So in order to make this thing unitless, we need the concept of distance. We have to kind of differentiate the same thing in order to get that. If we are using degree, which is a weird thing, and the other side is that cosine is this x value right here. See, this is cosine. Could write cosine. right? You don't want this to be distance over some degree. It has to be distance over distance. That's why we do not use degree in calculus. Does that answer that question? Okay, then let's do this. Let's review what this absolute value of x was. You remember what this was? Okay, let's start right here. This is x if x is positive, and negative x if x is negative. That's what gives you the v, correct? I'm gonna let that sit there, but oh, this is done by a computer, so I can do things like this. Ah, that was convenient. The same thing now. What happens if I divide everything by x? This becomes 1 and this becomes negative 1a. So that thing just means 1 or negative 1a. Gives you that distinct graph. Okay. This thing has a graph looking like this. We'll let that sit there. Now we are ready to tackle this problem. So derivative of absolute value of u, and u is some kind of function of x, okay? Let's start doing this. So we have u, absolute value. Well, we can still do this, right? This is either u or negative u, eh? Depending on whether I'm going to leave some space. U itself is positive or u itself is negative. Still with me? Now I'm going to divide everything by u itself. So far, so good? So far, so good? Okay. Now, and then I'm going to take a no, I jumped the gun. Sorry. I have to take the derivative of this, right? Before I divide. Okay. Now let's take a derivative of this. So if I take a derivative of this, and derivative of this, and derivative of this. So far, so good? And then this, of course, becomes u prime, right? Say yes.
Yes.
And this thing becomes negative u prime?
Yes.
Okay, so can we combine these two? I mean, it's u prime or negative u prime, right? This is your big hint right there. So we need 1 or negative 1. So why don't I write this thing like this? Right, this thing itself is either 1 or negative 1. You know what I'm saying?